So for the remainder of this course, we're going to circle back to things that oscillate. And so we'll talk again about single coordinate oscillations, like remember the mass on the spring, but we'll include damping from the very beginning, and we'll also talk about driven oscillations, where we're pumping energy into the system at the same time that damping is removing energy from the system. Then we'll talk about coupled oscillators, where energy can be exchanged between different oscillators, and use the Euler-Lagrange equation to understand, or at least see how these equations are developed. And from coupled oscillations, we can start coupling together many masses to find a wave equation in the limit of an infinite number of masses. We can get a continuum wave equation, and then talk about some mathematical properties of waves. So the remainder of this course, in other words, is all about things that wiggle. And things that wiggle, mathematically, we write down in complex notation like this. Here we have a wiggle in time, with omega being the number of radians per second, and this is a wiggle in space, with k being the number of radians per meter. So wiggles in time and wiggles in space. And of course, single coordinate oscillations we describe as a wiggle in time. And these are really important. And to remind you just how important and how universal single coordinate oscillations are, here are some examples of single coordinate oscillations, or modes in other words. So this is a mode of the sun, and it's got a frequency of 5 by 10 to the minus 4 Hertz. This is a very low frequency oscillation. And here we have an oscillation of silver nanoparticles. So here we have light coming in, hitting one of these little nanoparticles here, and causing the electrons to jiggle about, and the electrons jiggling give light radiation. And the frequency here is 6 by 10 to the 14 Hertz. This is 10 to the 18 times faster than the solar oscillation. And here are nuclear vibrations, and again, a million times faster than this again, and this is like the water drop model of the nucleus of an atom that has oscillations at this frequency. So same sort of physics, single coordinate oscillation, in other words single modes, covering huge range of timescales in the universe. And to start to understand how some of these oscillations work, one of the notations, one of the mathematical tricks we're going to use is complex notation and phasors. And this is something you've seen before, but I'm going to reintroduce it here for revision and put it in context of the work that we're about to do. We can convert between complex exponential notation and trigonomic notation like this, and back in the other direction like this. We can convert between radial and Cartesian coordinate systems like this, and there's a relationship between complex numbers and Cartesian coordinates because you can represent complex numbers on a Cartesian plane, and these are relationships between the trigonometric functions and the Cartesian coordinates. Some other useful trigonometric relations are these, which you've probably seen before, and sometimes if you're stuck, Mathematica can help, and there are some functions here that I've highlighted that can help with manipulating complex and exponential functions and trigonometric functions. Phasors. It can be very helpful to think about complex numbers in a geometric way. And we can do that because complex numbers are easily represented on a Cartesian plane with the real part on the x-axis and the imaginary part on the y-axis. So for example, we have two complex numbers, a and b, and we're going to add them together. We've got a being equal to some amplitude times e to the I omega t. We can imagine here, we've taken a picture of it, we've frozen it in time, we've got some phase here, omega t, which can vary in time, but it's just fixed in this diagram. And b, e to the I omega t plus delta, so there's a phase shift between a and b, delta. Well, we can add them together and we get c, right? So what's a plus b? Well, it's c. And we can write c mathematically as a plus b, e to the I delta, with this common factor e to the I omega t. So straight away what this tells us, if we have two oscillating functions with the same frequency and we add them together, we get a new oscillating function with the same frequency. So adding two frequencies together that are the same gives us something else with that same frequency back again. Let's go on and consider this sum c, a plus b e to the I delta, e to the I omega t, as being equal to some amplitude, little c, times e to the I omega t plus phi, where c is some real amplitude. So this is our c here, we've got a phase omega t plus phi, and we're looking for the magnitude of this vector, which will be this number c. How do we find it? Well, we can find c and phi by setting this equation here and collecting real and imaginary parts. So here's the real part, expanding the complex exponential using this expression here. And the imaginary part looks like this. And we can solve these simultaneous equations to find c and phi. So we do that, we get an equation looks like this. So we square these two equations, add them together. We can pull out a common factor of c squared here, and we get cos squared plus sine squared, which is equal to 1. And this gives us an equation for c squared. And for phi, we can divide these two equations and find tan phi like this. Considering now the real and imaginary parts of this equation here, what we can find is equations that relate the sum of two cosine functions of the same frequency and some phase difference with different amplitudes to a single cosine function with a single amplitude and a phase. And similarly, if we're adding two sines together, then we get a single sine with an amplitude and a phase phi, with c and phi defined above. Wherever we see a sine or cosine function, we can, if we want to, replace it with a complex exponential. And to get a physical number back from that complex exponential, we just take the real part to get a cosine function, or the imaginary part to get a sine function. So, for example, we could have two functions x1, x2, that cosine functions with some phase difference between them. We could equally write that as two complex exponentials, like this, e to the I omega t, e to the I omega t plus delta. And we could add these together, or we could add these together. Adding these x's together, we have some very complicated expression like this, which comes from the mathematics on the previous slide, where we add two cosine functions together, or the real part of this. So we can just write down the real part of this number here. And so writing this down and then taking the real part doesn't take up as much space. So oftentimes it's easier just to do things in complex exponential notation. That's why we like it so much. Now, they both work, and you can just decide which one you prefer. I should also mention here that in general, the superposition of n sinusoids of the same angular frequency is a sinusoid with the same angular frequency with some change in amplitude and phase. So this result here, we have two sinusoids added together. We could add n of them together, and we get some net amplitude and some phase, but the same oscillation frequency.